Right, so I've been working in Saturn for quite some time now with Vesa and a few other people, so I'm going to talk about our work in Saturn. And then Clément will talk about what he's working on, which is verifying Saturn data structure. So Saturn is a collection of concurrent safe data structure for OCaml5. With OCaml5, you have this new type of concurrency, like competitive concurrency, where you can have multiple threads or multiple domains, as we call them in OCaml, that are working in parallel. And the thing is, implementing a data structure is not easy, right? Like writing an hash table is not something that is pretty hard. And when you try to do that in a way that this is going to work with multiple domains, trying to access this in parallel, then it kind of becomes a mess. It's pretty hard. And so the intent behind Saturn is to avoid you this mess, is to provide some already well-tested benchmark, optimized and even verified concurrent safe data structure. And so when I was writing this slide, I was like, well, they are probably not going to take my word for it. Maybe I need to show them something that shows that this is hard. And so what I did is that I went on GitHub and I searched for the word atomic in the code written in OCaml. Because when you are using the atomic module, you are probably trying to do some multi-core programming. And I stumbled on this implementation. No shame on the author here. It's, the whole point of that is to show it's not easy to do, and I try to anonymize it. So the idea is that the author needed on its queue with a size function, like a function that gives you the number of elements in the queue. And we don't have that in Saturn. Like the queue don't have a size function because it's actually pretty hard to do. But the author tried to do it the way you will do it in a sequential way. So they define a type T, which is a record with a size and the queue. And the size is an integer that is going to be accessed by multiple domains, so it's protected under an atomic. And the queue comes from a supposedly concurrent safe library, so Saturn. So nothing to be done here. And then you do something, or like the things that you will expect to do. So when you push, you increase the size. When you have a pop, if you find something in the queue, you decrease the size. And if you find the queue to be empty, you reset the size to 0. So nothing is illogical here, right? But if you try this test, it's actually going to give you some surprising result. So this test, you have two domains that work in parallel. One is doing one pop, the other is doing one push, and once they are done, you do one additional pops. So at this point of the code, your queue is empty, so your size should be 0. But if you run it 10 to 20% of the time, you are actually going to get a size of -1. And if you look at where the author was trying to do here, he was just trying to add a size function, which is something very basic, right, to a very common data structure, a queue. So something that looks very easy to do, and still there is a mistake in it. And even worse than that, you could have written this test and never saw the bug. And this test is specifically written to catch this bug because I knew about it. So in a real application, you will probably have written a more general test and never find this bug, or maybe once, and then have a hard time to actually reproduce it. So this is one of the main reasons why this is hard to do that. But you might have already know about it. That is what hard to do. So maybe when you are writing a concurrent safe data structure, you go to the literature and you try to find algorithms that do what you want to do. So you could do that. For example, if you search for trade safe stack, you will find the Trevor stack. It's a pretty simple implementation to do. It's not a lot of line. It's basically just stating that stack is an atomic list. So no need to look at it, it's working. It's perfectly fine. But if you are trying to do that, it's probably because you are trying to do some multi-core programming, so you are probably trying to have some good performance. And so this is a benchmark of this, what I call an atomic list, which is just the Trevor stack. So in this benchmark, you have just one domain that are working in parallel. One is doing pushes, the other is doing pops. And we are looking at the number of messages over time, so we want this number to be high. So the number by itself means not a lot, so we can compare it to what you get if you do the easiest way to do a concurrent safe stack, which is taking the standard array stack and putting a mutex around it, right? So this is better, this is twice better, so that's nice, right? But if you look at what we have in Saturn, it's actually way better. And the stack is Saturn. is a traverse stack. But even something that simple needs some work to do, to be done to be actually efficient. And we have already done this work in Saturn. So hopefully at this point, you actually want to have a look at the repository. So what will you find in it? So in Saturn, we have multiple queues. We have the very classical Michael Scott queue, which is a multiple producer, multiple consumer queue, so normal queue. But we also have these queues that work only in a specific configuration, like the single producer queue, single producer, single consumer queue, that will only work if you have at most one domain pushing at any given time and one domain popping at any given time. If you have two domains pushing at one time, then it's not going to work the right way. It's going to give you some unexpected result. And the reason for this type of queue is that when you know about it, when you are writing the algorithm, and you have this type of restriction on what the domain can do, then you can basically take very large shortcuts. So this is essentially for performance. We also have work stealing the queue, which just talk, like the previous speaker just talked about it. So it's used in scheduler like the main slib. We also have a stack, an hash table that is actually not here, but not in Saturn for now, but Vesa did all the work. It's already in Picos, so it will be in Saturn very soon. We also have a skiplist and a bag. And if you need anything else, please ask for it. Open an issue on Saturn and ask for it, because what we want is to provide you with what you need, and we need to know about it to do that, right? And so if you need a size function for a queue, for example, you can open an issue. Well, now we know that you need it, but yeah. I also wanted to ask that most of these data structures are log-free. I won't go into the definition of log freedom, but this is a progress property that is very nice to have. So we are trying to have all our data structure log-free, but this is not always possible. Like a blocking queue, for example, is not going to be log-free. And so we have two libraries. We have a library that is called Saturn log-free that contain only log-free data structure, and another one that is called Saturn that contain everything. So I told you that our data structure are well tested. And to do that, we have two main tools. We have Lean and STM that you can find in the multi-core test repository. And this library enables us to test for correctness and linearizability. Again, I won't go into the definition of linearizability, but Clément is going to talk about it. But it's basically in properties that when you have it, it makes it easier to get to reason about the behavior you have. The code have. So it's a nice property to have. We have that on all of our data structure, and we check for it with STM. STM is, by the way, a very nice tool that will generate for you random tests, so you don't even have to write tests with it, which is great, right? We also have deque. Deque is a model checker, so for deque, you have to write the test. So for example, you could write the same type of test than the one that I showed you before, so you could have a test where you have two domains working in parallel, one is pushing, the other one is popping, both just once, and then when they are finished, you do one more pops. And at the end of that, if you are in the same implementation I showed you before, you expect the queue to be empty, so the size to be 0. And so you give that to deque. You state that you have a size of 0 at the end, and what deque is going to do as a model checker is going to check for all the interleaving in between the call to the atomic library made by the domain, the two domains that are working in parallel. And so the thing is, if you do this test in deque, the test that I showed you before, in 100% of the case, you are going to catch the bug. So this is great, right? And it's even going to give you the faulty interleaving, which is pretty good. By defect, by side, like a bonus that you get with deque is that if you test something that is not log-free, then it's never going to finish because it's going to generate an infinite number of interleavings. So if your test finish, you have kind of a good indication that your data structure is log-free, which is great because it's a very hard to prove property. Before I show you some benchmark, I wanted to talk about how we optimize our data structure. This work has been mostly done by Vesa. So if you have questions about it, I will be happy to hear about it, but Vesa will have the answer. So to improve our data structure, one of the main ways to do that is to reduce contention. You can obviously reduce contention by improving your algorithm, right? Like if you have a queue, for example, you may want the push and the pop operation to access two very different parts of your data structure, so you won't have contention in between this operation. But you can also reduce contention by preventing false sharing, which is now easier to do with the make contented functions that we have in the atomic module. There is obviously a lot of other ways to improve performance, like removing indirection, removing fences, like all this type of thing. And what we have tried to do in Saturn is to push our data structure as far as we could to see how one specific algorithm and one specific implementation in OCaml can go in terms of performance. And to do that, sometimes we were not able to not break the type checker, so not use magic. But this is still great to have some kind of limit of where we can go with an implementation. And furthermore, this has also been a way to test if one specific optimization actually is an optimization, is actually improving something. And this has been a way to, like a source of information for to add new language feature in OCaml. So you have right now an open PR made by Clément to add atomic record fields in OCaml. So yes, a benchmark. Finally. So this is a benchmark for queues. So you have 4 different queues. The green one is the unsafe one, the one using ops magic. The yellow one is the one that you, like the normal one in Saturn. I didn't precise, I forgot in the previous slide, but so we have this unsafe data structure in Saturn. They are called unsafe because this is this experimental data structures that are using ops magic. But you can find some of them in the repository, in the library. And so you have the yellow one, this is the normal queue. The red one is the standard library queue protected with a mutex. And the blue one is just the standard library queue without mutex, so it's just for one domain. And what you can see is, yes, very optimized with OpsMagic queue. The unsafe one is the best, but the normal one in Saturn is still pretty good, especially compared to what we could do, which is protected, which is use standard library queue with protected with a mutex. So it's nice to have that. It's not really the case for one domain, and the reason for that is that writing a concurrent safe data structure that is also log-free, it's a lot of overhead, so we are working on improving that for one domain, but for now, this is what it is. And this benchmark has been launched on my computer, which is an Intel computer, and just as kind of a small overview as what you can, that's the mess that you can get if you work on that. This is the same benchmark launched on Vesa's computer, which is an Apple with ARM CPU. And yeah, the unsafe version is way, way better here. So yeah, there's quite a lot to think about and to tell, which I won't say today. So yeah, this is Clément's part now.
Hi everyone, can you hear me? Yes. I am Clément Allain. I am a PhD student at Inria Paris. And my role in this work has been to introduce formal verification in Saturn. Is that okay? Right. Thank you. So okay, so I'm Clément Allain, and yeah, I introduced formal verifications in Saturn, and well, testing concurrent algorithms is hard because you have to cover a wide space, and with many possible alternatives. And so formal verification is also quite difficult, but it can be trusted. So what I've done is use the iris concurrent separation logic, which is fully mechanized in ROC, to specify and verify data structures from Saturn. So far, mainly concurrent stack, queues, and bags. So all this work is mechanized in ROC. So the first step is to translate the Saturn algorithms into ROC. So actually what we do is translate them into a deeply embedded language living inside ROC. So here you can see a simple push function from an assumed stack module implementing a concurrent stack. And at the bottom you can see its translation. It's a deeply embedded translation. So I hope you will agree with me that it is pretty much the same code, except now binders are quoted, right? And actually this transformation is manual as I'm being, but I am working on a tool to fully automate it, right? So once we've done that, we have our algorithms in ROC, we can specify them. So as Karine mentioned, the standard correctness criterion for concurrent objects is linearizability. Roughly speaking, linearity states that all concurrent operations should atomically take effect at some point during their execution, and we call this point the linearization point. And here you can see, well, in Iris, the way we do that, the way we prove this, is using what we call atomic specifications. So you can see the atomic specification of push. And what happens is, basically, it looks like a standard or triple with actually two preconditions and two pass conditions. So the two conditions inside curly brackets are standard as in all triple. So basically, they must be respected by the color of the operation. And the two other conditions, that's interesting, are they specify what happens at the linearization point. So basically, here you say that atomically during push, you transform the logical model of the stack from values VS to values vconst VS. Right? And crucially, this relies on the fact that we are working in a SC, in SC, so in a sequentially consistent memory model. Of course, you might be shocked by that, since you may know that the OCaml24 memory model is relaxed. I haven't time to talk about it, but I have some slides in case you have questions. I just want to say that it is possible. There is prior work on that, and it's future work. Right. So to finish this brief overview, I would like to give an idea of what the proof actually looks like in work. So, well, I claim that the main points, like the essence of the verification of concurrent data structures like those of Saturn, is to design a concurrent protocol. And what I call a concurrent protocol is basically a set of logical constraints that you want to enforce on your data structures to try to constrain its behavior. So here, to enforce the concurrent protocol of our stack, we write this stack-inf protocol, stack-inf predicate. So basically here it says that T, the instance T, is actually a memory location that always at any times points to a list of values that is actually the logical model of the stack, right? And I claim that given this predicate, you can verify this specification of push at the bottom. I will end it here. Thank you for your attention. I'll take questions.
To both of you, I'm sure we will also have questions here. We have time for a few of them.
So in some sense, the OCaml community is very new to doing all of this concurrent programming. And there's an enormous amount of work in other ecosystems trying to build best-of-breed concurrent data structures, both lock-free and not lock-free. And I wonder if you guys have done any looking at what are like the absolute best, you know, C++ and Rust and whatever kind of implementations for hash tables and queues and whatever of various kinds, and how the kind of implementations you're looking at here stack up against those.
I have just a few ideas on how to answer your question. Like, for example, the MySQL and the Traverse stack are used in most of the other libraries that are doing concurrent data structure in other language. So this is why we are using this implementation as well. For some of them, we actually, Vesa did actually some comparison with, like for the single producer, single consumer queue, we did a comparison with an implementation in C. And it's not good. Like the OCaml version is not as good as the C implementation. So yeah, we are trying to find a way to improve that and to go where they are. But this does it answer your question, right? Does it?
I think it gets some of the way there.
Some of it, yes. Right. Straight.
Maybe a related question is, so when you are implementing such like a concurrent data structure and you take one off the shelf from, I don't know, a paper or a different language, and you find out that it's not as efficient as you would like to be in OCaml. What are the tools that you use to try to find out what is wrong and or what to look for? Like, are there any specificities of OCaml that you have to look for that make it hard to make those efficient? Or
yeah, do you mean if it is inefficient or if it is not working?
Not inefficient.
Good question. Do you have a good answer to that, Vesa?
Yeah, so the way you have to implement these things is that you have to know how the hardware works, because it's all about cache coherence, basically. So every time you read or write memory, it has an effect on the cache coherence protocol. And once you understand how those things work, you can sort of figure out how to make things that run fast. So that's the short answer.
But so if something works fast in C, it doesn't mean that doing the same in OCaml will work fast, or does it? Or
as far as it's possible to do the same thing in OCaml,
okay.
then it should work the same performance-wise. Of course, there's some minor details like integers in OCaml have the extra bits, so there's a little bit of overhead there, and there's one big performance difference comes from write barriers, garbage collection write barriers. So some algorithms are much slower in OCaml, especially those that use arrays. So that's one thing to watch out for. But basically, it's the hardware is what mostly determines the performance.
Okay, thanks.
All right, I have a question for you, Clément. I had no idea part of Saturn was verified. That's great to hear. How much of it is verified in this day?
So not everything so far. I would like to cover pretty much everything. But so right now, as I said, it's stacks, queues, and bags. There's also the work stealing queue that well, it's I need to finish the full mechanization, but it's on paper. And I am also working on the skiplist, and then there is the hash table.
Yeah, what he is not saying is that obviously the skiplist and the hash table is way harder to do. It's way more like line of code to prove, so it's a lot more work.
Actually, I don't agree.
Oh, okay, we will talk about that.
No, it's more lines of code, but it's like less difficult than, say, the work stealing deque.
Interesting work. There was a bunch of work done in Haskell about implementing sort of dual versions of data structures and doing provability of that. I wonder if you've thought about, or whether it's possible to extract the code from Coq into OCaml and then compare it to the optimized OCaml version. Have you thought about doing that?
I'm sorry, can you repeat the question, please?
So you've got an optimized version of the data structures, and then you've proved that they're correct. Have you tried extracting the OCaml out of the Coq version and sort of using those as a comparison for correctness?
So okay, the question is, can we?
Can you extract? So you've proved things in Coq. Can you extract that OCaml code out of Coq? And is there any value in doing that and comparing it to your optimized version?
Okay, so the direction we have right now is OCaml from OCaml to Coq. I also thought about the other direction. So that would be from rock to lambda, because basically reconstructing types is not a good idea. So what you could do, but I guess that would require a bit of engineering to basically plug lambda module inside a bunch of OCaml ones. So yes, that would be possible. Is that an answer to your question? Yeah.
Thank you.